The universe's grand finale might be closer than we think. Our universe has a story. It began roughly 13.8 billion years ago. We've long wondered how it will end. For decades, the prevailing theory painted a picture of a slow, quiet, and lonely death, trillions of years in the future. But that future may have been drastically shortened. New evidence hints that the very force pushing the cosmos apart is starting to weaken. Instead of expanding forever, the universe might be destined to slam its cosmic brakes, reverse course, and collapse in on itself far sooner than anyone ever imagined. To understand this dramatic shift in thinking, we first have to appreciate the cosmic mystery known as dark energy. For most of the 20th century, astronomers debated the universe's ultimate fate. A key set of calculations by Russian physicist Alexander Friedmann in 1922 showed that the universe's destiny was tied to its overall density. If there was enough matter, its collective gravity would eventually overcome the expansion that started with the Big Bang, pulling everything back together in a fiery big crunch. For a time, this seemed like a plausible outcome. But in the late 1990s, observations of distant supernovae revealed something astounding. Not only was the universe expanding, but that expansion was speeding up.
This acceleration couldn't be explained by matter and gravity alone. There had to be an invisible, repulsive force at play, pushing space-time itself apart. Scientists named this mysterious influence dark energy. It's now believed to make up nearly 70% of the entire energy density of the cosmos, yet we know almost nothing about it. The simplest and most widely accepted explanation has been that dark energy is a cosmological constant, an intrinsic, unchanging property of space itself. In this scenario, the universe would continue to expand faster and faster, leading to a big freeze or heat death. In this distant, trillion-year future, galaxies would be so far apart they would be invisible to one another. Stars would burn out, all heat would dissipate, and the cosmos would fade into a cold, dark, and empty void.
However, recent and incredibly precise maps of the cosmos are starting to challenge this picture of a constant, unwavering dark energy. The Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI, two monumental projects involving hundreds of scientists, have created the largest three-dimensional maps of the universe to date. By charting the positions of millions of galaxies and quasars over the last 11 billion years, they can track the history of cosmic expansion with unprecedented accuracy. When this data is combined with other cosmological observations, intriguing hints emerge that dark energy might not be constant after all. The results suggest that its influence may be evolving and perhaps even weakening over time. While the data hasn't yet reached the 5 sigma gold standard of a definitive discovery, the evidence is strong enough to have prompted physicists to seriously explore new models for the cosmos. One such new theory proposes a radical new identity for dark energy. Instead of a single, constant force, it might be a combination of two competing elements. The first is a field of hypothetical ultralight particles known as axions. Axions have been theorized for decades to solve other problems in particle physics and are also considered a candidate for dark matter. In this new model, a universe-spanning axion field is currently the dominant force, providing the repulsive energy that drives the accelerated expansion we observe today. But there's a hidden component, a negative cosmological constant. While Einstein's original constant represented a repulsive force, a negative constant would act like a subtle, persistent gravitational pull, trying to rein the universe in. The theory suggests we are living in a temporary phase where the axion field's outward push is easily winning this cosmic tug-of-war. But this dominance is fleeting. As the universe continues to expand, the axion field is predicted to slowly dissipate, losing its strength. Over billions of years, its influence will fade into insignificance. When that happens, the underlying negative cosmological constant will take over.
The consequences of this switch would be profound. The universe's expansion would not just stop accelerating, it would begin to slow down. Eventually, it would halt entirely before beginning the long process of reversing course. The cosmos would start to contract. This would be the start of the Big Crunch. According to this new model, this dramatic turning point could happen in roughly 10 billion years. The collapse itself would be a slow-motion reversal of the Big Bang, playing out over another 10 billion years. Galaxies would cease their rush away from each other and begin an inexorable journey back together. As space itself shrank, galaxies would start to merge, and the universe would grow hotter and denser. In the final moments, the temperature would become so extreme that stars would evaporate, and atoms themselves would be torn apart before all of existence is finally crushed back into an infinitely hot, infinitely dense singularity.
If this timeline is correct, the universe would have a total lifespan of approximately 33 billion years. Given that we are currently about 13.8 billion years past the Big Bang, this would mean our universe is already more than 40% of the way through its existence. It's a sobering thought, but it's important to remember that this is still a highly speculative theory. It's a compelling mathematical framework designed to explain some subtle anomalies in our best observational data, but it is far from proven. This Big Crunch scenario is just one of several possibilities for the universe's ultimate fate. Another violent end is known as the Big Rip. In this case, dark energy would be a phantom energy that grows stronger over time. This would lead to a runaway acceleration where, in the distant future, the force would become so strong it would overcome gravity, tearing apart galaxies, stars, and planets. Ultimately, it would become powerful enough to rip apart the very atoms that make up matter.
And then there is the most sudden and unpredictable ending of all: vacuum decay. Quantum physics suggests that our universe's vacuum may not be in its most stable, lowest energy state. If a bubble of a true, more stable vacuum were to appear anywhere in the cosmos, it would expand at the speed of light, destroying everything in its path and rewriting the laws of physics as it went. There would be no warning and no escape. For now, the long, slow, big freeze remains the most widely accepted scenario. But the tantalizing data from projects like DESI suggests that the story is not yet settled. Future observatories will refine these measurements, telling us with greater certainty whether dark energy is truly constant or if it is indeed changing over time. The answer will determine whether our cosmos is destined to fade into a cold and quiet darkness, be torn asunder, or collapse in a final spectacular crunch, perhaps even setting the stage for a new beginning in a big bounce. The final chapter of the universe is still being written.